So here are your 3-5 notes. We're going to make sure you know what your learning targets are. So your learning targets for today are to classify polygons, to calculate interior angles of polygons, and to calculate exterior angles of polygons. Just remember, interior is inside, exterior is outside. So the first definition you have is a polygon. This is kind of, this is a lot to define, so I think what I'm going to do is I'll type it for you. It is a closed plane figure. Sorry. Oh, okay, never mind. I evidently am not going to type it for you. So it is a closed plane figure, and we might kind of run out of space, and I'm sorry. With at least 3 sides. I'll clean this up for just a second. Those sides are segments that intersect only at the end point. So they can't cross. Oh, that's an at symbol, sorry. Endpoint. This should all be in that polygon box, by the way. And there's no adjacent sides collinear. Sorry about that pop-up. No adjacent sides collinear. So that means that there's no sides that are kind of on top of each other, right? You couldn't have 1 side, 2 sides, 3 sides, 4 sides, and then another side that landed right on that same line, even if it was a little bit longer. That's what they're saying there. Okay, for your pictures, this is a polygon. All of my sides are straight, they're segments. They only intersect at the endpoint, and it's closed. I couldn't drive a car in there. Okay, these are examples, not a polygon. I'll do it in a different color. This would not be a polygon. And then if I did a little semicircle, that's not a segment, that's rounded. This is not a polygon. It's open. I can drive a car in there. Okay, it has to be closed. This is not a polygon, because by definition, your segments of your polygon can only intersect at the endpoint. This segment is intersecting kind of midway through. Okay? Kind of go through the rest of them. Maybe. Alright, I'm going to get rid of all of that just so you have more space to write. Your next definition is a convex polygon. That means that there are no diagonals with points outside the polygon. So pretty much, that's a great definition, but what's happening is if it's a convex polygon, everything kind of points out. When they're talking about diagonals, diagonals are lines that connect vertices. So there's a diagonal. There's a diagonal. A diagonal would not be here, because that would just be a side. So here's another diagonal, here's another diagonal, another diagonal, right? There's a nice little star. None of those red points, none of the diagonal have points outside of the polygon. Therefore, it is a convex polygon. Okay. Another way to think about this is kind of thinking about it opposite, the concave polygon. A concave polygon has at least one diagonal outside the polygon. So this kind of is like if you had a square, kind of like, ooh, pretend those are straight lines, right? That's kind of like a cave. If I were to do some diagonals, specifically this one right here, that has some diagonals outside of the polygon. Okay, now a couple ones. Equilateral polygon, all sides are equal or congruent. So let's just do some random shapes, and I'm trying to make them all equal, and I'm not sure how good I'm doing. Because I'm not measuring these, I need to show you that I wanted them to all be congruent, all to be the same measure. So I'm going to use tick marks. They each have one tick mark. That means that they're all the same. Equiangular means that all sides, all angles are equal. So we'll do a similar shape. And again, this isn't necessarily true on this shape, so I'm going to use this and tell you that all of these angles, even though I have not measured them and I cannot prove to you that they are all congruent, I wanted them to be. Okay? Your last one is a regular polygon. Regular is equiangular and equilateral. So this means all sides are equal and all angles are congruent, have the same measure, are equal. So when I go to draw this one, I'm just going to do a square because that's nice and simple, right? Well, I say that. All of these sides have the same measure, and all of these angles would be equal. If this is really a square, these would all be 90, of course. But, okay. I'm trying to remember. I thought there was something else I wanted to make sure you're okay with. Are you okay with exterior angles? I'm just going to add that here. Just when it comes up, so you have something else to refer to. I'm just going to give you a picture. Exterior angles of a polygon are just outside. But if you were to draw, let's say, a triangle, to get the exterior angle, you have to extend the sides. So what I mean is this segment would then be extended. Here's an exterior angle. This bottom side would be extended, creating an exterior angle. This side would be extended, creating an exterior angle. Those red angles are what would be classified as exterior angles. Okay, this one. Your first example says name the polygon, then identify its vertices, sides, and angles. So to identify or name a polygon, you're just going to list the letters that you see. They need to be in order. You can't jump around, but you can start anywhere you want to. I chose D. I don't know, I think probably just visually that's kind of where my eyes were drawn to first, like reading a book. You could have started wherever you want. If you wanted to, you could have said K, H, right? I don't have to go in the same direction. T, B, G, M. That would have been fine. Something that would not have been fine. I could not label this polygon M, K, right? I'm kind of going from here to here. Then jump over to D, and down to G, and then, oh yeah, I still have an H there and a B. That's no good. You need to make sure they're in order, so when someone starts, they kind of know the order in which they need to go. Okay? The second part of this question says, identify its vertices, sides, and angles. Okay. Might run out of room, I'll be honest. My vertices are P, H, K, because vertices are just the points where the segments touch, M, G, B. These are my vertices. sides would be BH, and because they're segments, I'll just do a single line above. HK, KM, MG, GB, and finally BD. So there's my sides. Angles would just be the vertices, only I'm talking about the angle they're referring to, right? Angle H would be right there. Angle K would be right there. So angle D, angle H, angle K, angle M, angle G, and finally angle B. Kind of monotonous, but there you go. Okay? Your next one, if I was you, I would pause the video right now and take a second and kind of try the quick check on your own. Okay, so to do this, it says 3 polygons are pictured. Name each polygon, its sides, and its angles. So I would have polygon ABE, talking about that triangle. Its sides would be AB, BE, EA. Its angles would be angle A, angle B, angle E. Whoops, sorry. There we go. Alright. The next polygon I see is BCDE. Its sides would be BC, CD, DE, EB. And finally, my angles would be angle B, angle C, angle D, angle E. My last and final polygon would be the whole thing. I'm going to do that over here. So I would have A, B, C, D, E. And I would have side AB, side BC, side CB, side DE, and finally EA. My angles would just be those points. So angle A, angle B, angle C, angle D, and finally angle E. Okay? The next example is still talking about classifying polygons, but now you're just talking about convex or concave. So here, this would be a convex polygon, because there's no place to kind of go in, right? If I were to do my diagonals, none of them would land on the outside of this polygon, right? Remember, a diagonal cannot be an already created side, right? That one's not connected. That one's not connected, all right? And then by number of sides, so 1, 2, 3, 4, 5, 6. So a convex hexagon. Okay. Over here, this would be concave. I could do a diagonal right here that would be outside of that polygon. So it's a concave. And we'll count the number of sides. 1, 2, 3, 4, 5, 6, 7, 8. Concave octagon. Alright, so let's see what's going on down here. Here's a formula that will tell you the interior sum. Okay, this is interior. It'll tell you if you add up all of the angles inside a polygon, what you will get. So it says, find the sum of the measures of the angles of a 15-gon. So according to the formula, I'm going to put in the number of sides, which is 15, subtract 2, it will always be 2, and multiply that by 180. I will always be multiplying that by 180. 15 minus 2 is 13. 13 times 180 will get you 2,340. So remember, that's all of the angles in a 15-gon added up. Okay? So pause here and take a minute for your quick check. Okay, so if I was going to do the 13 gone, I would follow the same steps. I would just put 13 in there. So technically I'm doing 11 times 180. Right, because I want the sum of the interior angles. And that would get me 1,980. Again, that is the sum of all of the angles and a 13 gone added up, right? Sum is when you add. The next one says the sum of the measures of the angles of a given polygon is 720. How can you use, not sum equals n minus 2 times 180 to find the number of sides of a polygon? I would just put the 720 in for the sum, that's my known, and keep my n, my number of sides, as a variable, oh my goodness, because that's what I'm trying to solve for. So I would divide both sides by 180. That's 720 divided by 180 will get you 4. And then I would add 2 to both sides. So 6 is n. A polygon is a 6-sided, it's a hexagon if it has 720 degrees inside. Alright, your next one. Now we're going to actually calculate some of the interior angles of a polygon, each angle instead of the sum. They want angle y. They want this angle right here. So this is 1, 2, 3, 4, 5 sides. 5 minus 2 times 180 will get me the sum. You may also just know some of these, right? 5 sides, a pentagon. You might have that memorized. Excuse me. So 540 is the sum of the angles inside of a pentagon. Well, I know that I have a 135, a 90, a 90, a 90, and then this y left over. So I'm going to take 540 and subtract the knowns. So 135, I have 390, whoops, no, that's not a 90. 2, 3, I'm subtracting all of those things, by the way. And if I do that math out, you're going to get 135. So the measure of angle y is 135 degrees. Pentagon ABCD has 5 congruent angles. Find the measure of each. I'm going to definitely take from the work that I've already done, save us some time. If I'm talking about a pentagon, as I was up here, I already know that it will have 540 degrees inside. If all of the angles are congruent, if it's equiangular, I'm going to just divide that by 5. 5 will go into 540, 108 times. That means that each angle measure is 108 degrees. Remember, as you're watching this, if you ever want to pause these videos and you have questions for me, please let me know. So here's your exterior angle. We kind of talked about that at the beginning of the video. See, those 1, 2, 3, 4, 5 are the exterior angles. Here I have a shape inside of a box, and they've labeled the angles of the triangles that kind of are making up the box. It's packaging pretty much. And they're asking you to find the measure of angle 1 in each foam triangle. Since these triangles are all the same, I just need to find angle 1 once, and they will all be congruent. Okay, so I have a triangle. I know that this is 90. I could also say, well, if I could find angle 2, it would help me, right, for this triangle. Excuse me. Also, if I knew what this angle was, the inside of that polygon, and there are many ways to do this, by the way. This angle, would you agree that red angle and the blue angle must add up to 180 because they're making that line? So I'm going to find the inside angle of this. 1, 2, 3, 4, 5, 6. It's 6 sides, so 6 minus 2. And I can use this because I know that this is a regular polygon. All of the sides and all of the angles are equal. So I can use this idea of dividing by 6. So that would mean 4 times 180. I'll have 720, so there's 720 degrees inside of that, and I'm going to divide that by 6, so I can know what one of those is. So the measured angle 1 will be 60 degrees. Right? And I should have made that red, I'm sorry. That's angle 1. Alright, my quick check, take a moment to try that on your own. Okay, they want to know, find the angle of measured angle 1 by using the exterior angle theorem. And if I look at this, here's a side extended, and there's that. So angle 1 is an exterior angle. Exterior angles are always 360, no matter how large the figure is, and I can show you a proof for that. So there's 6 sides, means that there's 6 exterior angles. All of them are congruent, so I'm just going to do 360 divided by 6, and I'll get 60 again, which is what I wanted, because that's what I had up here for the measure of angle 1. I've just gone about it a different way. Find the measure of angle 2. Okay, well, I know that angle 1 is 60 degrees. I know that's 90, and angle 2 is the third angle of a triangle. So I'm going to go 180, subtract 60, subtract 90, and I'll get 30 degrees. So the measure of angle 2 is 30. And now they're asking, is it an exterior angle? Well, it looks like it because it's on the outside. But let's really look at what's happening. An exterior angle by definition is when you take a side of a polygon and you extend it, right? So like, let's take this side. I'm going to extend it. Okay, angle 1 is an exterior angle. Angle 2 is made up of this side, and if I extend this side, it does not create angle 2. Another exterior angle would be right there. This side here that's creating angle 2 is not an extension of a side of the polygon. This is just a random line that they've put there. That is not an extension of this side. So angle 2 is not an exterior polygon, excuse me. Your independent work is page 161, 2 through 26 even, 33, 38, 40, 47, 73. As always, please let me know if you have any questions.